A very good day, everyone. I hope you are doing absolutely fine. So, this is the last topic of our last module, time series. We have already covered the theory on time series, and as I said earlier, it's a huge topic and it cannot be explained in just one video or even in 2-3 videos. But I have given you the basics and the direction to move on further. So, in this assignment, I will just be explaining the step-by-step process that we had studied in the previous video. So, without further ado, let's get started with our assignment. First, we will create a time series object using ts command in R. So for this, we will be using hotel sales data. So let's read the CSV file and store it in hotel_sales. Then let's see the structure of the data. There are 3 variables, as you can see: month, year, and sales. Now to work with time series, we need time series object. So we will convert it using the ts function. TS function requires a dependent variable. So our dependent variable is sales, then the start year, that is 2004 given in the data, and then frequency, which is equal to 12. Now frequency is something which is not simple to decide. We often use it as 12 when we have data of multiple years. There could be scenarios where there are multiple seasonality. Then we have to think which one is the most important. There are advanced methods to tackle this problem and can be explored further. But for now, we are taking frequency is equal to 12. And then we'll store it in the variable hotel_sales_ts. Now you can see the explanations given here that we have just discussed. So that is how we create a time series object. Now the above example was just to show you how to convert the data into time series object. We will now be using air passengers data for the rest of our assignment, which is already a time series object. So now we will see the stepwise explanation of time series analysis. So basically there are 2 major steps. In step 1, we will model the deterministic components. So first we will test for trend, then we will estimate the trend if it is present, then we will eliminate the trend. After that we will test for seasonality. Then we will estimate the seasonality if it is present. Then we will eliminate the seasonality. And then we will forecast the deterministic component. So these are the same steps that we had discussed in the theory as well. Then in step 2, we will model the residuals using ARIMA modeling. So in step 2, we will first check for stationarity and identify the order of differencing as applicable. After that, we will identify the order of ARIMA based on ACF and PACF plots or based on the AIC metric. Then we will check for constant variance and normality assumption. Then we will forecast the residuals using the best model. And then the last step, we will give the final forecast, which will have the deterministic component as well as the residual component. So let's start with step 1 and model the deterministic components. So first we will read the data. It is already available in R. So we will use the data function and then put the name of the data in the argument to call it from the library. Then we can store the data in the variable AP. And after that we can make a plot. So just by looking at the plot, we can observe that there is a presence of trend and seasonality. But we will follow these steps and carry out the test to determine trend and seasonality. So in the next step, we will test the presence of trend. So first we will install the DevTools package. DevTools is used to develop your own packages. Now I have already installed it, so I am calling the library directly. After that, we will install the trend season package. The trend season package is available on GitHub website. It was developed by Abhishek Umrawal. He happens to be my teacher. So he has developed his own tool and it is available for free to use. So we can install the package and then we will load the library. And then we will check the trend using the ro.test function. So we will pass the data air passengers through it. and then we'll get our results as shown here. Now we'll refer to the explanation to understand the output. It says as p-value is less than 0.05, it means the trend is present. Also, number of discordants is less than the expected number of discordants. Therefore, the trend is increasing. And now we will use the moving averages method for estimating the trend. So first we will load the library TTR that has the moving average function. Then we will use SMA function to find the moving averages and store it in the variable ma12.trend. We will use 12 here as the number of periods over which we will take the moving average. This data is of several years and is divided over 12 months in each year. So selecting 12 is a more sensible period. Now we can plot the air passengers data and then add the points of the moving average, which will give us our trend. So we can see in the plot, the points here represent the trend. Next step is to eliminate the trend. So for eliminating the trend, we will simply subtract it from our data. Then we will run this and store it in the variable dtrend. After detrending the data, we will proceed to next step to check the seasonality. So for testing the seasonality, we will use Friedman.test. We have Friedman.test function. So we will give our detrended data as the argument and mention the seasonality period as 12. So basically for monthly data, we take seasonality period as 12. Then we can run this. And here we have our output printed. Now we can read the explanation given here. First point says the p-value is less than 0.05. Hence seasonality is present. Then second point says we can now estimate seasonality using small trend or large trend method. And then we will be able to decompose. However, R already provides a package STL to do all the decomposition itself. The above method was just for understanding the steps in the process. So STL stands for seasonal and trend decomposition using LOES. LOES is a method for estimating non-linear relationship. We'll not go into its detail and we'll directly use the function STL. Also note, STL handles additive decomposition only. So we can transform the data using log transform if we want to use multiplicative decomposition. Now we can move on to the next step. As explained above, we can skip step 1.5 and step 1.6 of the above procedure and instead use STL command to perform decomposition and then make the forecast. So to use STL function, we need data, which is air passengers, then s dot window, which is equal to 12, and then t dot window, which is again equal to 12. We will see in the explanation below why we have mentioned these two arguments as 12. But first we will store the output in the decomp variable. And then we'll plot it. Now you can see the plot. All the components have been decomposed and are plotted separately. Now let's read the explanation given here. S dot window, which is for seasonality, could be set periodic or based on the seasonal pattern. In our case, seasonal pattern exists yearly. You can refer to the air passenger plot. Therefore, we are using it as 12. The next argument was t dot window, which is the trend cycle component change. Again, refer to air passenger plot above. Either we can mention 12 or we can leave it blank. It will automatically select it. Now there is one more function by the name decompose that can be used to decompose the time series. But STL is in general more efficient way of decomposing the time series. However, we will see how can we use decompose function to decompose the time series. So we can use the decompose function with our data as the first argument and then mention type is equal to additive. We can even mention type is equal to multiplicative as applicable. After this, we will run this and store it in the variable decom_add. Then we will plot it. And here you can see the time series has been decomposed. After that, we will decompose the time series again, but this time we will use the multiplicative model. So in the type, we will mention time is equal to multiplicative. Then we will run this. And after that, we will plot it. Now let's read the explanation for the above two plots. First point says, we can observe from the above plots that seasonality is present in both the model, that is additive as well as multiplicative. Then if you see the trend component is same in both the plots, you can go above and check it. However, since seasonality is not increasing in proportion with time, therefore we will use the additive model. So we can go back to the plot, and here we can see in the multiplicative model, the seasonality is not increasing with time. Hence we are going to use additive model. Now the last point says, we are using the series decomposed by STL function. Now there is no reason behind it. As I said earlier, STL function is a more efficient way of decomposing the time series. I use decompose function just for the demonstration purposes. So after this, we'll go to the last step, wherein we will forecast the deterministic component. So first we will load the library forecast. Then we will use the forecast function. Give the decomposed series as the first argument. In the method, we will mention naive because we are using a random walk method for forecasting. And then we'll mention the period as h is equal to 60. We will run this and then store it in the variable stf1. After this, we can plot the results. And here if you see the plot after 1960 is our forecast as shown with blue color. After this, we will forecast the deterministic components using random walk with drift. So here everything remains the same. The only change here is that in the method, we will mention RW drift instead of naive. We will run this and store it in the variable stf2, and then we will plot it. Now the portion in blue is our forecast. So that is how we have modeled the deterministic component. Now let's move on to the next step and model the residual using ARIMA method. So the first step in building an ARIMA model is to check the stationarity of time series. So we will load the T-series library, which has the augmented decay fuller test function. Then we will extract the residual from our decomposed time series. So simply subset the time series object from the variable decom, which has a decomposed time series, and then further subset the third column that has the residuals. We will store this in the variable residual. Then we will use the function adf.test and give the variable residual as the argument and run this to get our results as shown here. Now explanation of the output is given here. So let's read the explanation. The first point says, as p-value is less than 0.05, so we reject the null hypothesis, which says the series is not stationary, and we can conclude that our series is stationary. Second point says, however, if the series wasn't stationary, then we have had to make it stationary using the differencing. So we keep on doing differencing until it becomes stationary. We could use difference command for carrying out differencing. Now as we don't have to do the differencing, so the value of D in the ARIMA model is 0. Now we will only have to find P and Q. So let's proceed to step 2.2 and find P and Q. In step 2.2, we will identify the order of ARIMA based on ACF and PSCF plot or based on the other metric, that is AIC. So using ACF function, we can plot the ACF plot. So the first argument is the residual, and then we'll mention the title using the main command. So the title of the plot is correlogram -ACF plot. Then we can run this and our ACF plot is printed on the screen. Then we will use PACF function for plotting the partial autocorrelation. So again we will pass the residual as the argument and then give the title of the plot, and then we will run this, and here you can see the PACF plot is printed. Now let's read the explanation given here. First point says we can utilize PACF to get the AR order, that is P. So if the PACF cuts off after some lags, then that number is the order of AR. Then second point says if the ACF cuts off after some lags, then that number is the order of MA. Now if you look at the plots of ACF and PACF, then we can see that both plots have significant lags and we cannot conclude anything from it to identify the order of our model AR or MA. So in this case we will have to use AIC metric to determine the order of our model. So in order to use this method, we will first fit an AR model and find the parameters, that is coefficients and order, that gives us the best fit. So let's see how do we do it. First we'll create a null variable by the name aic.p. Then we will run the for loop from 1 to 6. So this 1 to 6 will be the value of p, that is basically the order of AR model. So we will create an ARIMA model using the ARIMA function. So the first argument here will be residual. Then in the order argument, we will mention the vector p00. So what will happen? Every time loop will run, the order will vary starting from 1 and it will go up to 6. Then we'll close the bracket. So every time we'll create a model corresponding to the order of p, and then we will extract the AIC value from the model using the $sign. And then we will store it in the variable that we had created above, that is aic.p. So along with aic.p, we have mentioned p within the square brackets. So when p is equal to 1, it will store the first AIC value. Then when p is equal to 2, it will store the second AIC value, and so on. So this way we can run this loop and then print our results as shown here. Now as you can see here, the lowest AIC value is for the 6th order. Now in the next step, we will repeat the process and fit the MA model and find the order of Q. So everything will remain the same, except that in the ARIMA function, we will mention order is equal to 00Q. And we will vary Q, which is the order of MA, from 1 to 6, like we did in the previous loop for the value of P. So we can run this loop and we can see our results are printed here. Now if you see the results, the best MA model is of the order 4 that has the least AIC. And then in the next step, we will fit an ARIMA model and find what parameters, coefficient and order give the best fit. So for this purpose, we will use a nested loop, as we will have to vary both P and Q. So let's see how do we do it. So first we will define a matrix AIC, which is a 5 by 5 matrix, because we are going to vary P and Q from 1 to 5. Then we will initiate the loop. First loop will vary P from 1 to 5. Then second loop will start and it will vary Q from 1 to 5. Then we will use the ARIMA function, give the residual as our first argument, and then in the order argument, we will put P, 0 and Q. So the value of D is 0 here. And then subset AIC using the $sign. Then close the loop. And then we will run it and print our results. Now if you see the table, we can see that for P is equal to 5 and Q is equal to 5, the lowest value of AIC is achieved. Now referring to the second point of the explanation, it says we usually try values of P and Q between 0 to 7 and then choose the lowest AIC model. So let's say if P is equal to 6 and Q is equal to 1, that would have been the next combination of P and Q after the last value of our table. Let's put it and see if it yields better results. So we will mention order is equal to 6, 0 and 1. We will run this and store it in the variable resi underscore model 2. And then we will extract the value of AIC. So if you see, the AIC value is decreased. So this means we should check the next value of P and Q as well. So what will be the next value as per our table? It will be 6 and 2 for P and Q respectively. So we will put 6 and 2 in the order as shown here, and then we will run it. So if you see, I have put a hashtag sign before this line. So let's read the explanation. The first point says when we try the next combination, it is giving an error which says non-stationary AR part. So to address the problem of stationary, we could use OLS to estimate AR coefficients. OLS is ordinary least square method. It will use the default maximum likelihood method in ARIMA. However, when Q is greater than 0 for MA, then OLS becomes infeasible. So without going further into details, just understand that we are getting an error which says non-stationary AR part. Therefore, there is no point of going further at this point. We will use P is equal to 6 and Q is equal to 1 as the best order of our ARIMA model. Now that we know which is our best model, so the next point says explain the output of the model selected. So our best model is stored in the variable resi underscore model 2. We can run this and print our results. And then again there is an explanation given here. So let's read the explanation. The first point says we get our coefficients, 5 coefficients for AR model and 1 coefficient of MA model, as well as other parameters in the model. Now standard error of coefficient tells us how precisely the model estimates the coefficients. So the smaller the standard error, the better the results are. So if we divide the estimate, that is our coefficient, by the standard error, we will get a t value. And then we can look up the t table to establish the significance. Larger standard error means lower significance. We can calculate standard deviation using standard error. So standard error is equal to standard deviation divided by square root n minus sample size. So from here we can calculate standard deviation if required. Then if you see in the last, we have sigma square in the output, which is basically the variance of error term. And then log likelihood is given, which is not of much importance to us, so we are leaving it. And lastly, we have AIC, which we have already seen earlier. Now we will move to the next step. It says check for constant variance and normality assumption. So if you recall, in the video where we had discussed theory, we discussed that for residuals, constant variance and normality is an assumption. So in this step, we will check those assumptions, whether they hold true or not. So first we will plot the residual plot to check for constant variance. We can simply use the plot function, subset the residuals from our model, and then run it to get our plot. So if you look at the plot, we can deduce that variance is constant. Then we will check the residual histogram to check for normality assumption. So we can use the hist function, subset the residuals from the model, and then run it. And here you can see the histograms printed. Again, we can see from the above histogram that it follows the normal distribution. Thus our two assumptions hold good. And now we can proceed to the next step, which is to forecast the residuals using the best model. So we will use predict function here. Give our model as the first argument. Then mention n.ahead is equal to 60, which means the number of months for which the forecast will be done. Then we can run this and store it in the variable pred underscore resid, which is basically predicted residuals. Now the last step is to add all the forecast, that is the deterministic component and the residual component. So our deterministic component is stored in the variable stf1. So we will simply subset the mean column of stf1 that has the forecast of deterministic component, and then add it to the predicted values of the residuals, which are stored in the pred underscore resid variable. Then we can run this and print our results as shown here. Now in the next step, we will plot the forecasted values and the observed values together on a single plot. But to plot this, we need one column that will have all the values from the first year till 1965, that means including the forecasted values. But if you see, our data or the observed data has 144 rows. So the air passengers data has 144 rows. And our forecasted data has only 60 rows. Because we have made the forecast for 5 years. So we cannot combine both of them using the rbind function. Therefore, we will first create a variable by the name of final and then combine both the columns using cbind function. So air passengers and final forecast we have combined here. Now what it will do is, it will combine both these columns irrespective of the length and will make the total length of each column equal to 144 plus 60, that is 204. So air passengers have 144 values from 1950 to 1960, and rest of the cells in the air passenger data will be filled with NA. And our final forecast has 60 values from 1961 to 1965. So rest of the values in the final forecast will be filled with NA as well. So this way both the columns will have 204 rows. After this we will replace all the NA values with 0. So we can use is.na function and then equate it to 0. This will replace all the NA values with 0. After replacing the NA values, we will create another variable. Let's call it plot underscore data. In this variable, we will add both the columns. That is column 1 and column 2 of our data, which is stored in the variable final. So this new variable will be used in the plot function to plot our observed and the forecasted data. What is happening here is that the first column of the data will have values from row number 1 to row number 144 because it contains the values from the air passenger data, and from 145 row number to 206 row number it will have 0 values. And the second column of the data will have 0 values from row number 1 to row number 144, and it will only have values from row number 145 up to row number 206. So when we will add these two columns, it will basically combine both the columns by adding 0 to all the values. And then we will use this final column to make the plot. We will use the plot function as shown here. And we will run this. And here you can see the plot is printed. So this plot has our original data up to 1960. And then the forecasted data from 1960 to 1965. Now I have included the explanation of the above code as well. If you haven't understood anything, you can read through it again. So that was the step-by-step explanation of time series modeling, wherein we have modeled the deterministic component as well as the residual component. Now the next part given here is the fun part, and I'm sure it will frustrate you because I was totally frustrated when I saw it for the first time. The next part says, all the above steps that were shown here were only for understanding. Now everything can be done in R in 2 steps. In step 1, we will decompose the time series. So we will use stl function. So we have already done it. We can run this and store it in the variable decomp1. And in step 2, we will straight away forecast using the forecast function. The first argument will be the decomposed time series. We will mention method is equal to arima. And then we will mention h is equal to 60. We will run this and then store it in the variable future. and then we will plot it using the plot function. And here you can see the plot has our observed data as well as the forecasted data for 5 years. This really fed me up when I spent hours learning all those steps, and then I realized that all those steps are not required and it can be done in just 2 steps. So going forward, you don't have to go through all those steps. You can simply decompose the time series and use the forecast function to make the forecast. Now one thing you might have noticed in the graph, that the order of ARIMA calculated by forecast is different than what we had calculated. And there could be reasons for this difference because we had done this manually. That's okay. We will go by the results of forecast only. So alright, with this we have covered our first assignment on time series. Now let's quickly revise what we have covered so far. So we first started by creating the time series object. Then we saw the steps involved in time series analysis, where we first modeled the deterministic component, and in the second step we modeled the residuals. So in the first step we saw how to estimate and eliminate trend and seasonality, but we didn't cover all the steps manually, as we used STL function for decomposing the time series. But just to give the idea, we did a few steps manually. Then we saw another function decompose for decomposing the time series. After decomposing the time series, we forecasted our time series using random walk. And then we modeled residuals using ARIMA, where we saw how we can find the order of ARIMA. And finally, we saw how the entire assignment can be done in just 2 steps, which involves decomposing the time series in the first step and then using the forecast function for forecasting the time series. So that was all that we had covered so far. Now there will be one more assignment on time series. So thank you for watching the video, guys. I'll catch you up in the next video. See you.